Welcome to the Solidity lecture. So Solidity looks quite familiar to JavaScript and it behaves very differently, so don't be fooled. Contracts, smart contracts basically look similar to classes, which we'll see in a bit, and functions are public by default. So there's a lot of, unfortunately, there are a lot of things in Solidity that are done by default that are implicit, which isn't very apparent at the beginning. So in particular for beginners, it's quite tricky sometimes to avoid security issues. So Solidity supports static typing, and every Solidity file basically starts here with this pragma Solidity and then a version number that you can specify, depending on which version you currently use. I can also recommend here this particular good resource that has some basic content on Solidity. So what is the smart contract lifecycle? I mean, typically what you do is you write the code in a high-level language, unless you absolutely want to write an EVM bytecode. And then you compile it to the EVM bytecode with the Sol-C or Solidity compiler. What you can then do is to deploy the transaction, and the deployed transaction is performed with transaction type create, as we've seen in an earlier lecture. And this is a transaction that deploys the transaction on-chain, and the contract code is then read-only from then onwards, so it's immutable on the blockchain. And what you can then do is to call the function with another transaction of the type call. So what's important is that the contract basically lives forever if there's no destruct function defined. You can actually define a destruct function if you'd like to. However, people might not trust your contract if you have a destruct function, because there might be an exit methodology or like an exit scheme that you define, and this might not always be suitable for everyone that's involved in this contract. So I just recommend you being very careful with a destruct function. There's no keep alive cost of a contract, so once you've deployed it, there's no cost for you as a deployer to continue running it. Basically, everyone who invokes the contract will pay for its execution. It's not the creator of the contract itself. So this gives no incentive to anyone to actually clean bad contracts or so, which has good sides and bad sides, right? You don't want contracts to be destructible by anyone or by a particular administrator, but you also don't want the blockchain to be filled with useless contracts that nobody need. So it's a bit of an issue. So contracts can call other contracts, and contracts can issue transactions, they can send funds, etc. So they really do have quite a lot of flexibility in what they can do. So the regular smart contract development really comes from Solidity, and you compile it to the EVM bytecode, which you can find more details in the yellow paper. And then there's the other alternative. You can for example, use Serpent. There's also Viper, they're different languages, and they also compile back to EVM bytecode. You can actually create like a higher level language to Solidity if you like to. That's your PhD there. Or if you really want to go godlike, why don't you just create like a competitor to Solidity that maybe alleviates some of its drawbacks. I can recommend you to check out ETHFiddle.com. It's quite a simple website, and you can see here you have an editor, right, where you specify the version of Solidity that you use, and then you define here a contract which is called simple store, and this contract does have two functions. So it has a function set and it has a function get. So think for a minute what these two do. Pause the video, and then we can discuss it together. Okay, so set is basically a function where if you call it with some value, it will set here a value, and this value is stored here within the contract. Now ask yourself, is this a storage variable or is this a memory variable in Solidity? Okay, and here you have a function get. And and this basically just returns the value that is stored in this contract. You can basically just try out this contract on this website. You can compile, and then it will have a field where you can set the value 5 and set it and set the value, and just try it out on this website. It's quite convenient. It's basically an emulator or a simulator for the Ethereum virtual machine. Now there's also another project that was initiated by one of your fellow Imperial students. It's the Flint programming language. It's basically a new language that's built on top of Ethereum, and it's basically there to replace, for example, Solidity. I'm not aware of its current development, but I don't think it's gotten very far so far. It's basically an alpha. It's basically currently an alpha version, but it's really promising to see such developments, and I would encourage you to try to develop other languages. So now let's go through the basics of Solidity, the types, right? So as in any programming language, you have different types. So in particular here we have a Boolean, we have uint 8, 16, etc. What's interesting is we have address types, right? And as the name suggests, this is an Ethereum address that you can use to pay to or use in your code basically. So you have as well bytes, mapping, etc. Right? So state variables that you store reside in storage, right? Okay, and remember maybe what was storage, what was memory, and which one was more expensive and why. Maybe you can recall this. Okay, now let's look at the Solidity function or functionality throw, right? So please check this code for a minute, pause the video, and then we can discuss it together. Okay, so I'm going to explain it. So here we have two state variables that are integers. We have a num candidates and a voting fee. And then we have two mappings from address to bool and from uint to uint. Okay, has voted and the number of votes. And then what we do have here is a function which is called cast vote. Right? So we can create a vote basically, and we can specify for which candidate we want to vote. Okay. So what this program checks here, it checks if message.value. So message.value is basically equivalent to the transaction that is incoming, that is calling this function here. Right? This is the transaction is basically equal to the message that is calling this particular cast vote transaction. And the smart contract will then check whether the value that's passed, if you check the transaction structure of Ethereum, is an ETH amount that is sent by the sender to this particular transaction, to this particular function of the contract. And the smart contract will check whether this is inferior to a particular voting fee that's defined somewhere, right? So if this message value is smaller than the voting fee, then return. So there will be no vote in that case. And then there's another check. So if in the map has voted, there already is a message.sender as a key. So that's here, this particular key, right? Then there's going to be a throw. So a throw is basically similar to return, but it consumes less gas. And then you can see here, has voted, right? You can see here, there's message.sender is equal to true. So before we actually record the vote, we are sure to mark this address as an address that has already voted. And then we can go here to num votes, and we can count the number of votes, or we increase the number of votes of this particular candidate, which we can count later on. Okay, and here we can tell you throw, make sure that only gas is consumed until here, right, and not the whole gas limit times gas price, right? This would be the maximum that you can pay. If, for example, you have you have an error or you run out of gas, then this is the gas that you pay. but if you throw, then you only pay the gas that you consume until there. But it's an error. It's an error indication. Yeah. State variables, right? So I mentioned state variables before, what kind of data types we have, and basically any variable here that you specify right after you define a contract, for instance, right? Here, any variable that you define here is a state variable, and they reside in storage, which is quite pricey. So keep that in mind. You don't want to store too many variables there if you want your contract to be cheap to be used. So what is a function? A function is basically here, for example, the function bit is a function that you can call within this smart contract. And by default, they're public. So this means everybody can call them. And you can define internal and external function calls. And there are several visibility parameters that you can specify. For example, external, which means it can be called from any other contract. It can be public, which is similar to external, but can also be called internally from another function within, for example, this simple auction function. It can be internal, so that it can actually only be called internally, and it can be private, so it's not visible in derived contracts. You can have inheritance among contracts as well. These are just some visibility parameters. Right? Now we come to modifiers. Modifiers are quite important. So modifiers are being used if you have a function, let's say the function abort, and you want this function to be only accessible, for example, to a seller. Then you can use a so-called modifier. A modifier is basically a security check or an access control check that is always executed before the actual function here gets executed. And as you can see, it looks quite straightforward. There's a require, and the require tells you that message.sender should be equal to seller, which is a state variable in the contract and which corresponds to an address that probably was populated before. And this basically means that only the seller or only the address here denoted or defined as seller can call the contents of the function abort. So yeah, modifiers are there to amend the semantics of functions if you want to tell it in a different way. So what about events? So in order to interface with smart contracts, you can write web interfaces, and if you want to write a web interface, it's quite helpful to define events, right? So for example, highest bit increased will trigger an event if this event happens, and then you can, for example, update your UI upon such event. So in the function bit, right, there's highest bit increased. There's, for example, .message send a message.sender, message.value is passed here, and then you can say this is triggering the event that you have defined here above, right? So in your function bit, if this happens, you can trigger this particular event. And in JavaScript, you can have a callback that basically listens to this event in order to update your web interface. Right? What's also interesting, which is another modifier that we haven't yet discussed, is here payable. And this means you can actually send funds to this particular contract through that address. If this is not defined as payable, you can't send funds to this particular function. So, do you remember the Namecoin lecture? Well, this is Namecoin defined in Solidity. So this is really just like maybe 20 lines of code. It's rather small, and it's really simple. You can define a particular cost to register a domain name. You can define a particular cost to update the domain name, and that's really it, right? So it's quite simple from a logic perspective, and this is the power of more complex smart contracts, because you don't need to deploy a whole new blockchain with a network layer, blockchain layer, consensus layer in order to define a new application. You just define this part of the code, and then you're done. So I let you play with this if you would like to. You can do this obviously in any environment such as ETHFiddle or other.